and welcome to Database Management Systems. I'm Jivita Christie, and in this video, I'm going to explain to you some additional relational algebra operations. These are necessary to reduce the size of your relational algebra queries, and if you would like to go through the fundamental operations, you can go through the previous videos. So let's begin with additional operations. The first additional operation we are going to see is the intersection, which is another binary operator like union and set difference. And it is used to take an intersection between two relations. So only what is common between the two will be kept. Everything else will be eliminated. And once again, it has the same type of condition as union and set difference. That is, both the tables should have the same number of columns and their domains, the domains of those columns should be same. So let's begin with this. Let's see an example with numbers. So if you have a set with elements 1 and 2 and another set B with elements 2 and 3, and if I do A intersection B, it will give me 2 because that is common between A and B. But you can also perform this with a set difference. If you do A minus bracket A minus B, it actually gives you the same result. See, you can see it here. If you do A minus B, it gives you 1. And then if you do A minus B, which means you're essentially doing 1, 2 minus set 1, it gives you 2, which is the same result as the intersection. So that's why intersection is an additional operation and not a fundamental one, because whatever you can do with intersection, you can definitely do it with set difference. The only thing you can see is a longer query, which when you're working with numbers won't matter much, because with numbers you just have two sets and your query size is not really that big to matter. But here you can see that there are a number of operations being performed are also more when you're doing it with set difference than with intersection. Let's see intersection with an example. And for this, I'm going to use the course relation, which contains the IDs of different courses, their names, the semester in which they were taught, and the year in which they were taught. Now, using this relation, let's answer the question of finding names of courses that were taught in both odd 2018 and odd 2019. And for this, first I'm going to write a query that fetches for me courses that were taught in odd 2018. And if you read it from inside, first I have applied the sigma operation, which simply fetches the rows which contain semester odd and year 2018. And from there, I'm extracting only the name column. And after that, I'm taking an intersection of this by writing the same query again with a different year this time, 2019. So how this works in practice is like this. You can see the query above generates two course names, which are DBMS and DS. The query below generates only one course name, that is DBMS. And when I take the intersection of the two, it results in only DBMS because that's common between the two. So this is how you can do an intersection. You can write an equivalent query to this by doing the same thing with minus. But when you do the set difference, you can see I have to repeat the query 3 times with different conditions. And this increases the size of my query as opposed to the previous one. But let's see how this is working. So the first query is fetching all courses from from odd 2018, which gives me DBMS and DS, from which I am subtracting the DBMS and DS and the subtraction of from this of the courses taught in odd 2019. And then once that is done, the result of that, of course, whatever is inside the bracket is going to give me only ds, and then ds is subtracted from what is outside, so it results in ddms. So it gives me the same result as intersection. Now let's see another additional operation, which is called natural join. It is a binary operation, and it eliminates the need to write the sigma condition with Cartesian product. So whenever we are doing a Cartesian product and we want to fetch those rows where some column is matching with another column, the values are matching, then we need to use a sigma condition. And if you want to remove that, then you can use a natural join. So once again, the database we are going to use contains instructor, it contains course, and it contains the teachers table showing the relationship between instructor and course. Now we're going to find the names of instructors and names of courses that were taught by those instructors. So in order to do that, with a Cartesian product, you had written a query like this in the previous video where I explained it. So we wrote the query in this manner. If we want to write the same query with the same result, which is this, with a natural join, you can write it like this. So all you need to do here is write down instructor, and then this bow tie symbol that you see here is the natural join symbol. So that gives you instructor natural join teachers natural join course. And what happens here is, because instructor and teachers, they have a common column, which is teachers I_ID. Because that I_ID column is common between instructor and teachers, that column is matched without having to write the sigma condition. And in the same way, because teachers and course have a common column C_ID, that is why that column is also matched without writing sigma condition. And then the pi condition which is present remains as it is. Now consider these two tables, instructor and teachers, just these two. Using these two tables, I'm going to show you some variations of natural join. So first of all, if you do instructor cross teachers, a Cartesian product, then you will get these 12 rows, because there are 4 rows in instructor and 3 in teachers. And then there are totally 6 columns. If you do a natural join between instructor and teachers, then all the rows that do not, where the ID of instructor does not match with ID in teachers, those rows will be removed. As you can see, those are marked red. So what remains is only these 3 rows, from which of course you can also eliminate one of the I_ID columns, since they are both having the same data. So once it is eliminated, this is what you have as a natural join without having to write the sigma condition. Now, the other operator that I'm going to talk about is the outer join operation. For that, I'm going to use these tables. This is a slight variation in natural join, and I'll show you how it can be useful. So I'm going to change the tables. The tables I'm using is one table contains subjects, and this shows you the ID of the course and the name of that subject and the department in which it is taught. And then the second one is the heads of those departments. So I have two departments, CS and PH, and Matthew and Thomas are the heads. Now, if I do subjects natural join heads, then this is what I get. Because between the two, there's only one department matching, which is CS. So that's why that first row just matches and gives you as a result this thing. But if you do another operation, a slight variation in natural join, which is left outer join, then it is going to perform a natural join, but it will include the unmatched tuples of the left side and will display them with null values of the right side. Let us see how that looks. So to do a left outer join, you will be using this type of a symbol. It's again a bow tie symbol, but on the left hand side, there are two small extension lines made. Now you can see it shows subjects, left outer join heads. And then once that is done, this is the table you will get as a result. The first row, which you are getting with natural join, remains as it is, but the next two rows are coming because even though they do not match with the right side relation, they are still there in the left side. So the rows with ME and EE will also be coming here, but for the column that is not present, which is head, for that we are going to use null values. So this is how left outer join works. The next one we have is right outer join. So the right outer join also performs a natural join, but this time the unmatched tuples of the right side relation will be uh, retained with null values of the right hand side. So let's see once again the same two tables, and this time it's a right outer join. So we have done extension lines on the right hand side, and this is what we get as a result. So CID and course, they are the two columns which are not present in the heads table. That's why both are null. And the row with PH and Thomas is retained because it is present on the right hand side and not on the left hand side. And obviously the first row remains as it is because it is matching. And the other type of outer join you can take is a full outer join, where unmatched tuples from both sides are kept with null values. So let us see how that works. You can use the symbol with a bow tie, the natural join symbol, with extension lines on both the sides. And the result of that is this table. The first row you are getting as a result of natural join itself, and this next two rows you are getting as a result of left outer join, because ME and EE do not match with any department in the heads table. The last row you are getting as a result of the right outer join, where PH is not matching with anything on the left hand side, and yet it is displayed with null values of CID and course. So you can see there are null values here also because head is not present in the subjects table. So this is how a full outer join works. The next additional operation that we are going to talk about is the assignment operation. It is used to make the relational algebra queries look neater and more readable. So that's its only purpose. And here is an example. This is a simple query that fetches names of all instructors with department IT and salary greater than 50,000. I could write it in a better way like this. I will use a variable a, and within it, I will store one part of my query, which is the sigma part. So this sigma part will only fetch the rows where department is IT and salary is 50,000, greater than 50,000. And then I can use A as an input for my next operation, which is pi operation, which is the project operation, within which I will pass A as an input. So A is nothing but a table now, which is the result of my previous query, which I can pass in the next one in order to get the same result. So if you write your query in this manner, you can write it in a more step-by-step approach. And that is why relational algebra is known as a procedural language and not a declarative language like SQL, because you can show which operation to perform first and which one to perform next. And that's it for all the relational algebra operations. And I have completed all fundamental ones and additional ones. There are even more operations, but if you know just these few basic ones, then you can actually answer any type of query that comes your way. So that's it for this video. I'll see you in the next one. Thank you for watching.